Okay, so lesson 7.3, we're going to really investigate e to the x. So if you look at y equals natural log of x, that of course has a very famous shape. We have this graph off to the side. This is the general shape of a logarithmic curve, specifically of natural log of x. E to the x, y equals e to the x, is in fact the inverse function. And I think you guys know that. E to the x, y equals e to the x is the inverse function of the natural log of x. And you see this right here. When you switch x and y, you would be able to see that that is the case. E is the number about 2.718. It is just like pi. It's an irrational number. It can be extended forever. Because e to the x and natural log are inverses, we know that if we took f of f inverse of x, we'll always equal x. The natural log of e to the x then would equal x. Similarly, even if you switch the order, f inverse of f of x would also equal x. So we have e to the natural log of x would equal x as well. One criteria though, x must be positive. Properties of exponents. Well, we can have e to the p times e to the q. We can add their powers together. We'd get e to the p plus q. If you're dividing e to the p divided by e to the q, this would become e to the p minus q. A power to a power, we multiply together. E to the p raised to the r is e to the pr. We're trying to be as good with time as possible. Here's an amazing theorem. The derivative of e to the x is e to the x. I'm going to perhaps prove this if we have time on the video later. Otherwise, we'll quickly prove this in class. That might seem amazing. You'd say, you mean you're saying you take the derivative of the e to the x function, you arrive back at the e to the x function? Yes, unbelievably. In a similar way, if we're taking the derivative of e to the u, that would be e to the u, where u is some function of x, chain rule will apply. Look at that. So I'll leave that proof towards later, but let's quickly jump into how we can start doing this. Let's say I gave you e to the cosine of 2x. Let's go ahead and take the derivative. Guess what we'd get? E to the cosine of 2x. But then we have to take the derivative of the cosine of 2x. Oh, good chain rule review. Wonderful chain rule review. What is the derivative of cosine of 2x? We'd get negative sine of 2x times 2. It's like a chain rule within a chain rule, isn't it? So real nice review. This can only help us as we prepare for a final and ultimately are preparing for that big test in the spring. So hey, just organize everything together and you get this nice and quickly. In a similar way, we can look at number 2 and we'd say, well, my word, now I have y equals x times e to the negative x squared. Let's just take a derivative. Your friends in AB calculus might have done this long ago, a good month ago or so, because what rule do you think we'd really need here? The product rule. We have, u would be x, and v, the other function, would be e to the negative x squared. Let's see, u prime, what's the derivative of u? It's just 1. Hey, what's the derivative of v? What would we get? E to the negative x squared. Ooh, chain rule here. What's the derivative of negative x squared? Negative 2x. Well, the beautiful thing about the product rule is it's uv prime plus u prime v. As I said before, it's almost like you can cross multiply here and add those two things together. Here's x times e to the negative x squared times negative 2x, and we'll join all that together in just a moment. And 1 times e to the negative x squared. Well, a negative 2x times an x is a negative 2x squared, e to the negative x squared. And then we just have plus e to the negative x squared at the end. Could you also factor out an e to the negative x squared? You could. Okay, we doing okay? All right, moving quickly. Wow, look at this. If you have the integral of e to the u, by the way, maybe this is making sense. This would really look more helpful if you did a u substitution, wouldn't it? And that's what we wind up doing time and time again. But hey, the integral of e to the u du would be e to the u plus a constant. So, wow, we look right here at example 3. And we'd say, wow, we have e to the 1 over x all over x squared dx. We think, where do we begin? What do you think we could do? Let u equal, what do you think? 1 over x. And 1 over x, of course, is x to the negative 1. I hope we've done enough derivatives with 1 over x to know that its derivative is really what? Negative 1 all over x squared. I mean, you can bring down that negative 1, and that's x to the negative 2. And here you go. We could solve for dx, multiply by x squared, and divide out that negative. And we'd have this. So dx is negative x squared du. And this integral then becomes e to the u. Down here's x squared. But my dx becomes negative x squared du. And the x squareds cancel. You are left with a negative 1. You can pull that negative out in front. And we're so close to being done, guys. So amazingly close to being done. So let's see here. As I take an antiderivative of e to the u, keep your negative out in front, is e to the u, and then we'll say plus c. Is that my final answer, though? Yeah, resubstitute in. Your u is actually 1 over x. And hey, look at that. There you go. Negative e to the 1 over x plus c. Yeah. Okay, so for our next problem here, it's a definite integral. We're going between 1 and 3. And you might wonder if we're going to do a little u substitution here, and we will. Guess what our u would equal in this regard? Negative 4x. And that means du would equal, what do you think? Negative 4 dx. And dx would be du all over negative 4. And that's fine. We could say I will have an integral of e to the u, and my dx will be a du all over negative 4. But my boundaries, those lower bounds and upper bounds, have to be adjusted. The 1 and the 3 are actually x values. So with this in mind, when x is equal to 1, and that's what we're seeing on the very lower bound, u is negative 4 times x. That's our substitution. So u would be negative 4 times 1. It would be negative 4. So this lower bound I'm going to write as negative 4. When x would equal 3, and that's on the upper bound right here, you'd say u would equal negative 4 times 3, and that would be negative 12. So then I'll have negative 12 up here. By the way, this might trouble some kids, because here's the main issue. Sometimes kids will say, well, wait a minute, Mr. Dobner, the smallest number, the tiniest number in the bounds is now on the top. And guys, that's okay. You could work it out in that order, and you'll definitely be okay. That would be perfectly all right. Look, I'm going to pull out a negative 1/4, but sometimes it still troubles kids. They look at that and they're like, oh man, that just doesn't look right. I want to see the smaller number on the bottom. And you know what? If that really bothers you, you can change that. You're always free to change the bounds. But when you do that, what's going to happen? Yeah, you got to change the sign out in front. So this would become a positive 1/4. I do want to be clear, though. Either integral that you see here, this step or the one before it, if you work it out, you'll be okay. You'll get the final answer to be the same. But look, I'm going to say this is 1/4. Here's the e to the u. That's your antiderivative. And here's -4 to -12. And let's just go ahead and work this out. Here's e to the -4 minus e to the -12. You could leave your answer like this. You can't combine e to the -4 and e to the -12. You could take reciprocals if you would like and make that 1 over e to the 4th and 1 over e to the 12th, but it's not necessary to do that. Okay? Tell you what. We did have an earlier question in regards to finding a constant. That's more or less what's happening here. You're introduced to solving a separable differential equation. And a separable differential equation is something we will talk about more in the near future. But suffice it to say, what that means is you could separate the dy and the dx. I could multiply both sides by a dx, so to speak, and all of a sudden you would get this. You see, when it says solve the separable differential equation, they're saying, please tell me what y equals. And guess what I'm going to do to find y here? I'm going to integrate. I'm going to integrate both sides. Now, the left side, if I'm integrating a 1 dy, what do you think I'd get with respect to y, of course? I would just get a y. Now, I'm sure some of you want to say y plus c. Let's hold off for that just for one moment. You could put a plus c right now, but tell you what, it's a constant on the left, there's a constant on the right. If we subtract the constants, there'd still be a constant somewhere. So typically what we do is we just keep the constant on the right-hand side. Guys, what I'd like to do right now is speed up the antiderivatives here so that we don't necessarily have to do a u substitution.